In this video, I'm going to introduce Newton's second law of motion and give you a simple example with a little bit of calculation going on in it. I'll give you a more complicated example in a following video, and yeah, we'll go from there. So Newton's second law, what it does is it quantifies. So this is a law that's going to let us calculate stuff. So it quantifies a prediction. It quantifies the relationship between what's called the net force on an object and that object's amount of inertia. The amount of inertia is also called, also known as, the object's mass. And mass, we're going to use the unit of the kilogram to start describing in the dimension of mass. Remember the net force, this is a vector, and we're going to use the unit called the Newton, which is symbolized with a capital N. All right, so the way Newton writes down the second law, it's actually using arguments of proportionality, and it's pretty amazing how simple this way of thinking about motion is. It's amazing. Newton's super smart. So what Newton says is that the acceleration of our object, so this is how the object's motion is going to change. So the acceleration is directly proportional to how the net result of how hard it's being pushed on. So directly proportional to the net force on the object. So it's directly proportional to this quantity, and let's be really careful. I'm going to be somewhat pedantic. So it's directly proportional to the size of this vector, so that's the magnitude, but it's actually also in the same direction and in the same direction. And so what we could shorthand write this and say that the acceleration vector is proportional to the net force vector, and so net force on the particular object. So that'll be the first part of the second law, but there's another part. It says that the acceleration, so I'm going to do this, I'm going to be a little bit pedantic again, is a vector whose magnitude is proportional to the inverse of the mass, the amount of inertia. So whenever you're inversely proportional, the bigger and bigger the number down here gets, the smaller and smaller 1 over the big number becomes. So the more and more inertia that an object has, the more and more difficult it is to give the object a certain acceleration. These two rules, right, you can see that I could have written this out with language, but it's quite fast to just do it in symbols. So here is one relationship between acceleration and net force. Here is another relationship between the magnitude of the acceleration and the inverse of the mass of the object. And you can summarize Newton's second law with a nice tidy statement or claim, which is pretty interesting. It's the claim that the acceleration of an object is equal to the net force on that object divided by the inertia of the object, or the mass of the object. And this is a way to write down Newton's second law right here. It's one thing to write down Newton's second law, but it's another thing to actually know how to use it. And that should be more of your goal, quite honestly. Like, people have this tattooed on them, and actually they have the wrong thing tattooed on themselves. Whenever you see this, you should be a little bit critical, because it's not just any old force that's equal to mass times acceleration. It really is the net force on the object. People say F equals ma, but that's not quite correct. I think it's better to put the little net. It's about the sum of all of the forces that act on the object. That sum dictates what the acceleration of that object is going to be, not just any particular force. Okay, so another thing that I'll mention real quick before I move on, I'd like you to notice how the units are going to go. So with SI units, this is a really nice system of units. I'll show you how nice it is. The unit that we use for acceleration, I may have mentioned it in an earlier video, is meters per second squared. So 1 meter per second squared in SI units is equal to 1 Newton divided by 1 kilogram. So the SI unit system just has the factor of 1 in front of all of the units. So this is the relationship. You could say that this is the definition of the relationship between the Newton, the kilogram, and the meter per second squared. Yeah, I'll say no more about that. So now I have a simple example to describe to you.